We throw this word learning around a lot when we talk about machines. It almost sounds like magic, right? We give a model a bunch of data, and somehow it just gets smarter. But what's really going on under the hood?
I mean, how does a model actually know if it's improving? Is it just randomly guessing? No, there has to be some kind of scoring system, right? Something that tells the model, hey, that was a good answer, or nope, that was way off, try again.
Well, that's exactly what we're going to unpack today. By the end of this, you'll understand that very scoring mechanism. It's truly the engine that drives all of machine learning.
So let's get into the core idea. And honestly, it's simpler than you might think. It all comes down to creating a scorecard for mistakes.
The best way to think about this is like a student studying for a big test. The model? That's our student. Every time it makes a prediction, that's like an answer on a practice quiz. The ground truth, that's the correct answer. The one in the back of the book. So what's the loss function? That's the grading method. It's how we score the student's answer. Now here's the twist. Unlike you or me taking a test, the goal here is to get the lowest score possible. A 0 is a perfect score. A high score means you were way, way off. So the whole game of learning is really just one big, systematic effort to get that score as close to 0 as possible. And that score has a formal name, a loss function. All it does is measure the gap between the model's prediction and the real ground truth answer. It literally just puts a number on how wrong the model was.
Okay, quick sidebar, because this trips people up all the time. You're going to hear loss function and cost function thrown around, sometimes like they're the same thing. They're not quite. The loss is the score on a single example. The cost is the average score across the entire batch of examples. So think of it this way. Loss is your grade on one math problem, while cost is your average grade on the whole homework or assignment.
All right, so if a loss function is our grading method, that raises a pretty important question. Which method do we use? Turns out it really depends on the kind of problem you're trying to solve. Let's start with regression problems, where you're trying to predict a specific number, like the price of a house or the temperature tomorrow.
For regression, two of the most popular grading methods are mean squared error, we just call it MSE, and mean absolute error, or MAE. The key difference between them is how they handle big mistakes. MSE hates big mistakes. It squares the error, so if you're off by a lot, the penalty just explodes. MAE is a bit more forgiving. It just takes the absolute difference, so a big mistake is just a big mistake. No extra drama.
Let's make this concrete. Take a look at this table. In that last row, our model's prediction was off by 20. With MAE, the error is, 20. Simple. But with MSE, we square that 20 and it becomes a whopping 400. Now look at the first row. An error of 5 only results in an MSE score of 25. You can see right away how just one really bad prediction can totally dominate the final score when you're using MSE.
So how do you choose? Well, if those big mistakes, those outliers, are something you absolutely cannot tolerate, then MSE is your friend. Think about financial predictions. A huge error there could be disastrous. It really punishes those big misses. But if you have some outliers in your data that might just be weird noise, and you don't want them to completely skew your model's training, MAE is probably a safer, more robust bet.
Okay, that's regression. But what about the other big category of problems? Classification. This is where we're not predicting a number, but a label. Think spam or not spam, cat or dog. For these kinds of problems, we often use something called log loss, or you'll also hear it called binary cross entropy. Now this one works a bit differently. It's not just about how far off the answer was. Instead, it compares two probability distributions. First, you have the model's prediction, like, I'm 80% sure this is spam. And you compare that to the ground truth, which is basically, this is 100% spam. And here is the absolute key to understanding log loss. It has a real kick. It doesn't just penalize wrong answers, it brutally penalizes predictions that are both confident and wrong. So if your model screams, I am 99% sure this is not spam, and it actually is spam, the loss score goes through the roof. This is really powerful because it forces the model to learn not just the right answer, but also how to be honest about its own uncertainty.
And believe me, this isn't just some abstract, theoretical stuff. Loss functions are the beating heart of pretty much every machine learning system you use every single day.
Think about it. The image classifier that tags your photos, the spam filter in your email, the recommendation engine that knows what movie you want to watch next, all of them are constantly being guided by a loss function working behind the scenes. And this is especially true for the large language models that are everywhere right now.
So when a large language model is learning to write, it's typically using cross-entropy loss, a cousin of the log loss we just talked about. And a great mental model for this is to think of the loss as a measure of surprise.
Here's how it works. For any given sentence, the model looks at all the words it knows, tens of thousands of them, and assigns a probability to each one for being the very next word. The loss function then looks at the actual next word from the training data and checks what probability the model gave it. If the model said there was only a tiny chance of the correct word appearing, but it did, well, the loss is huge. The model was very, very surprised. And the entire training process over and over billions of times is just about tweaking its internal wiring to be less surprised by how humans actually write.
So if you remember one thing, it's this. A loss function is simply the scorecard that tells a model exactly how wrong it is, giving it the map it needs to get better. And that brings us to the most crucial point. Choosing a loss function isn't just picking a formula from a list. It's the moment where you define what success even means for your model. You are translating a real-world goal into a mathematical target. So the question you always have to ask yourself is, does my loss function really capture what I'm trying to achieve? Am I grading my model on the right thing?